So how can we measure concentration of free calcium ion in a living cell? You can do this by using microscope-based fluorometry. This is a powerful method which one can use for measuring the concentration of calcium ion, magnesium ion, sodium ion, chloride ion or zinc ion, depending on which probe you use. You can measure the pH in the cell. You can also measure metabolic parameters like NADH or FAD, and you can also measure membrane potential if you use probes that are sensitive to changes in membrane potential. You can also measure signaling molecules like cyclic MP or nitric oxide if you have the right probe to detect these signaling molecules. And one can measure these parameters from a single living cell in real time without resorting to destructive biochemistry. In this sense, this is a powerful and convenient method. Let me tell you about fluorescence. One can talk about photophysics of fluorescence for hours, but this simple Yavosky diagram is a convenient way to illustrate fluorescence. There are some molecules called fluorophores which can be excited to a higher energy state by light, and these molecules then relax to a slightly lower energy state because of internal conformation changes, and then when the molecule returns to the ground state, it gives out light. The energy of the excitation light is higher than the energy of the emission light. In other words, the wavelength of the excitation light is shorter than the wavelength of the emission light. A microscope-based fluorometry system consists of a microscope, a microscope photometer, an adjustable iris to select a single cell, a viewing eyepiece to look at the cell, a filter holder that holds filter to filter the emission light, and a photomultiplier detector that detects the emission light. Some fluorophores are excited by one wavelength, but they give out light in two wavelengths. These are dual emission fluorophores. One common example is Indo-1, which is used for measuring calcium concentration. If you want to measure two emission lights, then you need to have two photomultiplier tube detectors, and you need to have a mechanism to separate the two wavelengths. The configuration of such a system looks like this. You need to have a microscope, you have a microscope photometer, adjustable iris as before, viewing eyepiece to look at the cell, then you need to have a dichroic mirror. This mirror reflects the short wavelengths and transmits the long wavelengths. This is also called a beam splitter. And you need to have filter holders for filtering the desired wavelength of emission light, and you need to have, of course, two photomultiplier detectors. For dual excitation ratiometric fluorometry, one needs to excite by alternating wavelengths, alternating at high speed. For example, when we measure calcium by Fura2, it is the fluorophore is usually excited by 340 nanometer wavelength and 380 nanometer wavelength. This is usually achieved by computer controlled high speed monochromators. Fura2 is usually excited at 340 nanometer and 380 nanometer wavelength, and emitted light at 500 nanometer is measured. Calcium bound form of Fura2 is most fluorescent at 340 nanometer wavelength excitation, and free Fura2 is most fluorescent at 380 nanometer wavelength. As calcium concentration increases, more and more calcium bound Fura2 is there, and the fluorescence at 340 nanometer excitation increases, and the fluorescence at 380 nanometer decreases. At 360 nanometer excitation, fluorescence of fluor2 is calcium independent. This is called isosbestic point of fluor2. In contrast to fluor2, which is a dual excitation wavelength ratiometric fluorophore, INDO1 is a dual emission ratiometric fluorophore. INDO1 is excited at 338 nanometer and it gives out light at 400 and 500 nanometer. As calcium increases, emission at excitation 400 nanometer increases and emission at excitation of 500 nanometer decreases. There are many calcium fluorophores suitable for different purposes. Some are suitable for measuring calcium beneath the plasma membrane, some are suitable for measuring calcium in the endoplasmic reticulum, and some are suitable for measuring calcium in the mitochondria. It is likely that many more calcium fluorophores will be developed in future.